before I forget, by the time we get out of lecture today, your next Canvas quiz will be available, and that is amine nomenclature. So we've already talked about that. You know everything you need to know about amine nomenclature by this point. The only other thing that I wanted to mention about this is, I don't know if you've noticed, but on Canvas, there is an amine nomenclature homework. So it's just kind of a handful of amine compounds for you to name. I'm not going to assign or collect that, but if you would like, you could do a little practice on that. There's a key posted to this as well. So you can work on this, check your answers on the key, make sure you're comfortable. And then whenever you are, go ahead and take the quiz sometime before our next lecture, okay? Does anybody have questions on that or anything else before we get started?
You said that for experiment 7, the UV spectra for the products are in the lab manual?
No, they're on Canvas.
Oh.
Go into the lab stuff module, so at the very bottom, and you should find a file that's called experiment 7 spectrum. Yeah, you can use those for the UV that you were not able to collect last week. Okay, so I did actually, before we jump back into material, just wanted to kind of give you a heads up on scheduling. So let's see, where are we? Today's the 28th, right? Yeah. Okay, so we're right here. So if you have a look, you are scheduled to have your next synthesis homework due on Wednesday this week. I think what I'd like to do is push that back. So I think what is going to work better for us is if we push that back to next Monday. Because first of all, I'm not sure that we are going to get through with all of the amine reactions today. And even if we do, that would give you a day to complete the synthesis homework, which is kind of a lot to ask, I think. So I think it'll just be a lot more comfortable pacing-wise if we move the amine synthesis, that's number 3 here, back to next Monday. And that will probably end up causing us to shift amine synthesis 4 to the Monday after spring break, which is probably then going to push the exam to the 20th. Okay, so that's what I am tentatively thinking, unless anyone has any major objections to this. Sound good? Okay, then we will plan on, and I'll let you know kind of exactly what's due when we go over to lab in the next hour and a half or so. But just wanted to give you a heads up. That's what we'll tentatively plan for then. Okay. Okay, so let me go ahead and start recording, and we can get going. Okay, so the last time we met, we were going through the reaction, or the synthesis of amines, rather. And I believe we were on number 5, maybe. Where we stopped, we were talking about the Hoffman rearrangement. And what we had said was that this was a really good way of making very hindered primary amines or aromatic primary amines. Right? Because up to this point, if you go back to the previous 4 methods that I gave you for synthesizing amines, they were all SN2 processes. Which means if you're trying to make a very hindered primary amine, we don't really have a good way of doing that. And so this Hoffman rearrangement kind of fills in a gap in our synthetic methods for us, okay? And the way we do this is you take I think we were going through the mechanism last time, but we didn't finish it. But what the Hoffman does is it starts with a primary amide, and it treats that with a molecular halogen under basic conditions. And what ends up happening is you end up rearranging this to give the primary amine with the loss of the carbonyl of the amide as carbon dioxide. So it's a pretty interesting reaction, it's a useful reaction, and I'd like to go ahead and finish off the mechanism of this now. Because as I said earlier, it's probably not immediately apparent how all of this happens. So let's go ahead, I think I'll go through the first part of it pretty quickly because we already did that last time. Where this is going to start is the base is going to grab a proton from the amide. So deprotonates there. Giving you the anion, and that will act as a nucleophile to go and attack the halogen. So nothing unusual there. We've seen nucleophiles attack halogens for a long time now. So we just end up with a halogen on the nitrogen. And the significance of that is that now we have a leaving group on nitrogen. Okay? And that's going to be useful for us in a later step. Okay? We're going to need that leaving group. And you'll see why in just a minute. Once you get the leaving group there, the base is going to just do that one more time. It's going to grab the other proton off the nitrogen, which is why you can only do this with a primary amide, because you mechanistically require 2 hydrogens for 2 subsequent deprotonation steps. Okay? If you had a secondary amide, for instance, you wouldn't have enough protons to do this mechanism. Okay? So in the second step, or the second deprotonation, you pretty much do the same thing. So we have the anion, and I'm going to just draw a resonance form of this because I think it'll be easier to see what happens using the second resonance form. But in the other resonance form, I'm just shifting a lone pair from nitrogen into the carbonyl like that, which would give me a structure like that. So what we're going to do in the next part of this mechanism is the actual rearrangement part. This is where things are going to start shifting. And the way this kind of gets precipitated is I'm going to reform the carbonyl. So imagine that for a minute. If I reform the carbonyl there, I can't just make the new bond without doing anything, because then that carbon, this carbonyl carbon, would have too many bonds on it. So I could just break the carbon-nitrogen double bond that I just formed, but that just gets me back here. So what is going to end up breaking here is the carbon to carbonyl to carbon bond. And the way that, I mean, it can't just break and send this off as a carbanion because that would be a terrible leaving group. So what ends up happening is this whole group is going to shift over to the nitrogen. And that is the point of the first half of this mechanism. That is why we had to put that halogen on nitrogen. We need a leaving group on nitrogen so this group can migrate over and then kick out the good leaving group. So this will just move over like so and kick out the good leaving group. It's a lot like that Pinnacle rearrangement that we looked at. You know, kind of like when we had the shifting benzene rings. It's a lot like that. But in the end, what you get is I'm going to have the carbonyl. That's going to be double bonded to the nitrogen. And now that nitrogen is no longer bonded to the halogen, it's instead bonded to the benzene ring. And this is what's known, this functional group is kind of a weird one that you probably haven't seen before. It's what's called an isocyanate. And the isocyanate is, it has a very, very electron deficient carbon on it. I mean, we've seen carbonyls attack, or excuse me, nucleophiles attack carbonyls for many months now. But this is even more electrophilic than a regular carbonyl because not only does it have the electronegative oxygen attached, it's also got an electronegative nitrogen attached. And so under the conditions of the reaction, the base that we have is going to come in and it's going to attack that center. And that's what we get as a result. And here we have a problem with acid-base chemistry. This species cannot exist in this form. It cannot exist because you have an N-, which is a very strong base, and you have a carboxylic acid, which is a fairly strong acid. So these two cannot coexist. All right, so as soon as this forms, there's going to be an immediate proton transfer as the strong base deprotonates the strong acid. So what we really get is a carboxylate and a neutral nitrogen. And it is at this point where we see the driving force of the reaction. The driving force of this reaction is the loss of the carbon dioxide. So you can see we just have to shift the electrons in like that, and that's going to break that bond, and out comes carbon dioxide. Now, we've seen this before. We've seen this as a very strong driving force before in reactions. The one that comes to mind most immediately is Wolff-Kishner, where we have a gaseous product. And I think I told you then, this is among the strongest driving forces in chemistry. Because anytime you're making a product that's a gas, it's kind of by definition, it's leaving the solution. And all you have to do is think about the Le Chatelier principle. What does Le Chatelier say about the continual removal of a product? Drives everything in the forward direction. Okay? So that's what we see in this step. And then the last remaining thing to occur is we just need to give nitrogen a proton, which we can do because you're doing this with water around. And so in the end, you have the primary amine coming from the primary amide.
Is that also a one-way arrow?
Yeah, it is, just because of the acid base, the pKa of the water compared to the pKa of the amine. Any questions on this mechanism, or how we might use it?
Yeah, this was my question.
Mhm.
So is it only for when we have the carbonyl group attached to the benzene ring?
Yeah, yeah, you have to start with an amide.
Oh, okay.
Okay, so let me give you a,
I have a
oh, go
question.
ahead.
Are there any clever ways to draw an isocyanate that we wouldn't recognize? Oh, that's an isocyanate?
Mm,
Because some of the other products had some interesting ways of looking that didn't look quite like.
No, not really. I mean,
Okay.
it's just gonna be, that OCN group, kind of, just double bonded to
And
each
does
other.
it have to have the benzene hooked to it as well to be an isocyanate?
No, it can be, that OCN could be attached to anything.
Okay, so it's just the OCN part that's critical?
Yeah.
Okay.
Professor, another question. So you said that when the nitrogen that has two lone pairs
Mhm.
is not gonna exist, so we don't have to write it down in the mechanism, or?
Well, you
It's
do,
not
it's just not gonna exist for any real amount of time. Because as soon as this forms, due to the extreme basicity of the nitrogen and the relatively extreme acidity of this proton, there's gonna be a nearly immediate proton transfer.
Oh,
So this thing exists, but just for a fleeting moment, I guess. Okay, so let's see how we might use this synthetically. Let's say I'd asked you to make that. So what should be immediately apparent looking at this amine compound is that we cannot use those previous four methods that I gave you. You know, for instance, you might think, oh, well, I know I can make amines through the displacement of a halide with a Z ion. Well, could we use that chemistry? I guess if we're trying to do it through a Z chemistry, we would need the halide, which would have to look something like this. And do chemistry like that. So obviously there's a problem there, right? You're never gonna do an SN2 reaction on a tertiary halide, so that is clearly not gonna work. Right, so we would need to start thinking about other ways of synthesizing this, recognizing that it is a very hindered tertiary amine. Or sorry, let me scratch that. It's just a very hindered primary amine. So think about how we could use the Hoffman for this. Okay, so if we're gonna use the Hoffman, we know we have to start with the primary amide. So I think our only choice here would be to do the Hoffman on that amide. Because remember, what the Hoffman does is it takes the primary amide, it cuts the carbonyl out, and then stitches together the remaining pieces, which would in fact give me the target that we're trying to make. All right. Any questions on that?
How do we make without species?
Oh, that's what I was gonna ask you.
Oh my.
So, how do we make this? Well, I don't know that, we haven't talked about it before. So to make amides, they come from carboxylic acids by way of an acid chloride, right? So the way you would make that, this particular one, is we would take an acid chloride and react it with ammonia. Okay, so we just do kind of a substitution reaction where the amine comes in, attacks the carbonyl, and ends up kicking out the chloride. You don't really know this mechanism yet, but don't worry about it. We'll learn about it in the upcoming chapters. But it is a specific type of substitution.
It's not SN1 or
It is
SN2.
not SN1 or SN2. But the reaction does work. Okay, well, how do you think we get to that acid chloride?
SOCl2.
Yeah? We would get to the acid chloride by taking a carboxylic acid and reacting it with thionyl chloride. Any questions there? I mean, yeah, you could, but I mean, if you use PBr3, you get an acid bromide, which, yeah, they're not really as, people don't usually use those very often. Yeah, the acid chlorides are much more common for acylation compared to the acid bromides.
And then going a step back, would we be able to use KMNO4 to get to there?
Yeah, sure. So it'd probably be the, I don't know, if it were me, I think I would probably do something like this. You know, imagine using that as a halide and then doing kind of Grignard chemistry, which would give you the primary alcohol, and then you could oxidize it to the carboxylic acid.
And the KMNO4, is that hot or cold? It's
You
hot,
do,
right?
you do, yeah, you do it hot because we
Okay.
want to oxidize it as much as we possibly can.
Okay.
Okay? Any questions on this or the? Mhm.
So, I'm not sure if I'm just forgetting something about how oxidation works, but, so with that primary Grignard bromide, right?
Mhm.
If you were to use KMNO4, would you still need an additional carbon?
Mhm.
So how would you have that?
Yeah, because you can't, there's
I guess you-
nothing here that could really be oxidized, you know? So, especially if you're trying to get a carboxylic acid, really the only place that's gonna come from is from the oxidation of or the most common way of getting to it is gonna be the oxidation of a primary alcohol. So we would need and if you count carbons, you've got 1, 2, 3, 4, 5 carbons there. This has 1, 2, 3, 4, 5, 6 carbons there.
That's where the Grignard bromide.
Yeah, so that's why we need a Grignard reaction to add an additional carbon.
Gotcha.
Okay, any other questions on this? Yeah, you did.
Is there no way to like turn it into an alkene and then go from there?
Turn it into an alkene. Well, yeah, I mean, you could easily eliminate this. You know, if you treated that with base, or even like a bulky base. but that still doesn't give you the right number of carbons. Right? So you could do a lot with that double bond, but none of that chemistry is really gonna allow you to put on an additional carbon, which you need, because again, this has 1, 2, 3, 4, 5, and this has 1, 2, 3, 4, 5, 6.
And you said Grignard with the formaldehyde, right?
Mm-hmm. All right. Any other questions on the Hoffman? Okay, then let's go ahead. So we're still missing a very important piece of this amine synthesis puzzle. Because we do know how to make kind of what I would consider normal primary amines. We looked at a bunch of ways of doing that through SN2 chemistry. We now know how to make hindered primary amines using the Hoffman. But so far, we have not seen any methods that allow you to synthesize the higher order amines. How do you make a secondary? How do you make a tertiary? And so that's what I'm going to show you now. I'm going to show you two methods that are much more general. And these will allow you to make any kind of an amine you want, primary, secondary, or tertiary. All right? So I think this is number 6. Yeah, 6. One of the ways we can do this, make any class of amine we want, is through the reduction of amides. So we just looked at how to make an amide. You know, if you wanted to make an amide, you simply add an amine to an acid chloride, right? So we talked about how to synthesize them, but if you want a primary amine, very simply, you start with a primary amide. So I would take my primary amide. The reducing agent of choice here is LAH. And the LAH, what it's going to do is it's going to add H- to the carbonyl and ultimately convert that to a methylene. So that would give us something that looks like this. So the primary amide gave the primary amine. Right. Notice also, my work up here is in water. Normally when we think about using LAH, we always do a step 2 acidification. We're not doing that for the same reason we didn't do that when we talked about amine synthesis last time. You know, if you were to use acid in your workup, you run the risk of protonating the basic amine, in which case it would be very difficult to isolate. All right, so how do we make secondary amines? To make a secondary amine, probably not too surprising, you start with a secondary amide. And use the exact same conditions, LAH, aqueous workup. And again, what you'll see is that the LAH can reduce the carbonyl to the methylene. So just as before, the secondary amide gives you the secondary amine. Lastly, if you want the tertiary, all you have to do is start with a tertiary amide. And other than that, everything's the same. So the tertiary amide gives you the tertiary amine. All right. Any questions on these? So this is a nice generalized method that will allow you to synthesize any class of amine you want.
Are we gonna practice making those amides? Because I'm not really sure how to do that either.
Oh, it's just the same way we did in the previous reaction. So the amide is going to come from the acid chloride with the corresponding amine. So if you wanted to make this tertiary amide, we would take that and then react it with that amine.
Do we need any reagents?
Not really. You just put them together.
together?
Most people will use pyridine. But yeah, that's pretty much it. The acid chlorides are incredibly reactive, so you don't really need anything other than them.
Professor, you know how on the exam says use a simple carbon chain?
Mhm.
How do we make secondary amine?
Well, the higher order amines get very repetitive because this secondary amine would have to come from a primary amine.
So you have to make the primary, then make the secondary, then make the tertiary. You have to just go through each
Mhm.
one.
Yeah.
So do we make it by alkylation?
No, you don't really want to make amines through direct alkylation because it's difficult to control. So, you could, so we're trying to make a secondary amine here, and at this point, the only way we have of making the secondary amine was
B,
right here,
which requires a primary amine.
which requires a primary.
So you just have to step.
Yeah, you have to kind of build it up stepwise. Okay, so let's see, what if we wanted to, let me give you practice here, what if we were trying to make this? So first off, what kind of an amine is this that we're trying to synthesize? Yes, secondary amine, so that tells us we have to use a secondary amide. So, I guess in this case, well, the carbonyl has to obviously flank the nitrogen in order to make an amide. So we could do that?
No.
Yeah, that really just does not look right, does it? Obviously, we can't do that because that carbon has 5 bonds on it, so that's a silly thing to draw. I guess then the only other choice would be that one. So that's the amide we would need, and yes, looking at it, it is a secondary amide, which should reduce to give us a secondary amine. So, to get here, remember to make these amides, we always make them through the combination of an amine with an acid chloride. So the acid chloride would be the 3-carbon acid chloride. And we would combine that with the amine like that.
So there's no loss of carbon dioxide at all?
No, not with this one.
That's fine.
The only thing that's lost is the chloride as the leaving group.
Oh. It's a little easier to keep track of them.
Mm-hmm. Yeah. Yeah, nothing's happening to the carbon skeleton. Okay. Any questions on how to use this amide reduction to synthesize amines?
I'm not quite sure I understand what's going on when you're making the amide. What kind of a reaction is that?
It's just a substitution. So the nucleophile is going to go in and attack the carbonyl. And don't worry too much about the mechanism, because we'll get into this when we study the acid derivatives here in the next chapter or two.
Okay.
But ultimately what ends up happening is the chloride ends up leaving as a leaving group.
Okay.
So yeah, don't sweat the mechanism right now because you don't know it, but we will, before your exam, you'll learn it very well. Okay, so the last way I'm going to give you for making amides is another generalized method. So it will allow you to make any kind you want. And this is a method that's known as reductive amination. And so what reductive amination does, it's kind of similar to reduction of amides, but it requires 2 pieces. So you're going to be adding an amine together. With an aldehyde or a ketone. By the way, what functional group would result from this? We've seen this reaction before. We looked at it whenever we were studying the chemistry of aldehydes and ketones.
Amine or enamine, one of them.
Yeah, you're right. Which one is it? Amine or enamine? Primary amine plus ketone.
I think it's enamine.
You're right. Yeah, we would make the imine, which for these reagents would end up looking like this. Well, clearly, that's not an amine. So what we have to do once you make this imine is throw a reducing agent in. Because if you reduce the imine, you see how that generates the amine. So the trick to using the reductive amination reactions is that the amine product is always going to end up one level higher than you started with. So for instance, in this case, you'll note we started with a primary amine. The product is a secondary amine. Because basically, the aldehyde or ketone that you're using here just ends up adding to the nitrogen as an alkyl group in the end.
Just a quick question.
Yeah.
Are there any reducing agents that we should know that don't work?
Well, there's one that is specifically designed for this. Okay, so, but it's a good question. Do you see, so nobody does this in two separate reactions. Like, no one is gonna combine these two together, get your amine, isolate it, purify it, characterize it, and then take it into a next reaction where you reduce it. Everybody just does this one pot. So you mix together the amine and carbonyl and wait till out pops the product. Okay, so do you see what the potential problem would be? Let's think about our current reducing agents. If you were just to use let's do sodium borohydride. Do you see a problem with this reaction?
You'd end up with alcohols.
With what?
You would end up with alcohols?
Yeah. Borohydride readily reduces aldehydes and ketones. Think back to the experiment 6, when you were reducing the camphor, right? That reaction took all of 5 minutes. So borohydride has no problem reducing aldehydes and ketones. And it's going to reduce long before you would ever get a chance of imine formation here. Your borohydride would reduce the ketone. And so what you would isolate is amines and alcohols from this reaction. So we cannot use something like borohydride. We need to use a weaker, more targeted reducing agent. Something that is capable of reducing imines, but not capable of reducing aldehydes and ketones. And the one that is used for this, that was designed for this, is one that's very, very similar to sodium borohydride. Instead, what we're going to use it's still a boron-based hydride reagent, but we are just going to replace one of the hydrides with a cyanide. And this is called sodium cyanoborohydride. So remember, the cyanide group is a very strong electron withdrawing group. So its presence here helps to kind of stabilize this anion a bit more. And because it's a stabilized anion, it's a bit less reactive. So the bottom line is that it's capable of reducing imines, but not capable of reducing aldehydes and ketones. So what it allows us to do is take the two starting materials, throw them in a round bottom flask with the cyanoborohydride, let it go for a few minutes, and then out pops the higher order amine product. So it's a really nice way, very easy way of making these amines. It's quite common. So let's see how we could use this. So I told you it was a generalized method. We can make primary, secondary, tertiary amines. So let's see that in action. So remember what I told you. Your product ends up one level higher than the starting material in all of these. So if our goal is a primary amine, what does that mean we have to use? Well, if you use, I mean, you could, but more specifically, what does that tell you about the nitrogen group? Yeah, it has to be a 0 order. Alright, so for instance, if we were trying to make a primary amine, we could. We just need to use the ammonia, the 0 order amine, if you want to think of it that way. Just think about what that would give you. Initially, that would give you this imine, which upon reduction is going to give you the primary amine. So we're starting 0 order amine, we're ending up primary amine.
Professor, next to the NH3.
Oh,
not-
that's just a scratch mark.
Oh,
Sorry. There you go. Now, a lot of people probably wouldn't exactly do it this way, just because ammonia is a gas, and handling gaseous reagents is just a pain. So one other way that you could possibly do this is instead of using ammonia, sometimes what they'll use is this thing which is called hydroxylamine. Hydroxylamine is a well-behaved solid. You don't have to worry about handling gases. You can just go and weigh it out on a balance and throw it in the flask, and you're good to go. All right. What if we wanted a secondary? Well, we kind of already looked at this one. That was the example I gave you at the very beginning. So if you wanted a secondary amine, we would need to use a primary amine. Because again, the product always ends up one level higher than the starting material. So we're starting with a primary, and we're ending up with the secondary here. All right. Finally, if you wanted the tertiary, that means we're going to need to start with a secondary. All right. Any questions on the reductive amination?
We don't need to say like step 1 and step 2, this is all just going in together.
Say that again, sorry?
We don't need to like do a step 1 and 2, they're all going in together. right?
Correct, yeah.
Okay.
You just mix them all together. Okay. So now you have plenty of methods to make any kind of an amine your heart could ever desire. So let's look at, before we leave the synthesis, let me give you one final example. So what if we wanted to do this? Take a minute and see if you can come up with the starting materials you would use for this tertiary amine. So there are a few ways of approaching this. I think what I would probably do, so we want a tertiary amine. So if we're gonna try to use reductive amination, that means one of our starting materials is gonna have to be a secondary amine. So, I don't know, we could roughly do something like this. Putting the two of those together with the cyanoborohydride would give us the tertiary amine that we were trying to make. But again, you didn't really have to, right? Any of the secondary amines that has two of the three things attached to the nitrogen would work here. All right. How do we make this amine?
So the other two ways would be with aldehydes rather than ketones, is that right?
One of them would be, yeah, because you would, in order to get the ethyl group on, in order to do that, you would react with an aldehyde.
Oh, but the other, okay, this would be it. Okay, I
How do we get to the secondary amine here? Yeah, do reductive amination again.
It's the same one for the sample of
Oh, yeah. Yeah, so we could maybe do something like this.
the other way.
How would we get the primary amine here? Yeah, that one you could do any way you want, right? I could just take bromopropane and react it with sodium azide and hydrogenate it, and that would give me this primary amine. Okay. So yeah, once you start looking at the amine synthesis that's gonna be due a week from today, I think you'll realize that it's not so bad, because a lot of it's just kind of repetitive stuff. All right. Any questions on the methods for amine synthesis here? Okay, then let's go ahead and leave that. And let's see what kind of reactions we can do with these. So most of these you've already seen. The first thing that we can do that we've already talked about is we can alkylate amines. Meaning if you take some sort of an amine and you react it with an alkyl halide, you can put alkyl groups on the nitrogen through SN2 chemistry. Now, I did warn you about this one. This is not a great way of making amines, generally speaking, because it's very difficult to control. So typically the only time you will normally see people do this is if you're trying to make the quaternary ammonium species. So the only time you would really ever want to do this is if you planned on treating that amine with an excess of the alkyl halide in an effort to get the ammonium species. Okay. So it is a little bit limited in scope that way.
So Professor, can we use, ethanol?
Oh yeah, you can use any alkyl halide you want.
Oh,
Yeah, so you could use ethyl bromide, for instance, and that would put 3 additional ethyl groups on there, whatever you want. Okay.
The quaternary is called ammonium.
Yeah, a quaternary ammonium species. All right, the other thing that we can do, which you've already seen, is we can acylate. Meaning, take the amine and treat it with an acyl chloride, and that's going to give you access to those amide compounds that we talked about. All right. The third thing we can do, well, probably want to rephrase that. The third thing that can happen. This is not usually something you set out to do, but what amines can do is they can oxidize. So you can ultimately oxidize them up to the nitro group. But this is not normally done. And the reason it's not normally done is because these reactions get pretty messy. Because there are multiple oxidation species along the way. So it's not like if you subject an amine to oxidizing conditions, you go straight to the nitro group. There are multiple stops along that path. So for instance, you have a series of functional groups. One of them looks like this. So that would be an oxidized form of the amine. We call these hydroxylamines. You can oxidize further to something like this, which are called nitroso compounds. And you can oxidize further to the nitro group. So the reason I say people don't usually set out to do this is because it is usually pretty messy and it usually gives you mixtures of all of these. You just have to, more than anything, be careful about anytime you're dealing with an amine, the oxygen in the air will actually oxidize amines over time. So you have to be careful with that. But more importantly, if you're doing an oxidation reaction, you have to be especially careful. In grad school, at one point, I was working with one of the nitrogen bases, the nucleic bases. And I think, I'm trying to remember now, I was trying to oxidize the sulfur actually to get to make a sulfone, and I kept getting some weird spectra. And what ended up happening is, yes, I was oxidizing the sulfone, but in the presence of this exocyclic nitrogen, I was also oxidizing it. So the point is, if you're trying to do oxidation reactions in the presence of amines, you typically have to protect the amine, because otherwise they'll oxidize too. Okay. Any questions on the first three of these reactions? Yeah, David?
Do we know how to protect amines?
I don't think you have learned that.
Okay.
Yeah. A lot of times they're protected just as amides, though. You just acylate them, and then you can hydrolyze the amide at a later time. But yeah, I don't think you'll need that information. It's a big business. I mean, there's a whole slew of different protecting group strategies for nitrogens. developed largely for amino acid and peptide synthesis, but you don't really need to know that for this class. Yeah, maybe?
The oxidizing reagents are they the same as the ones that we've learned for alcohols?
Pretty much, yeah. Okay, then let's go ahead, let me show you the next one. This is the Hoffman elimination. Tell Hoffman was a pretty busy man. He had his rearrangement, now he has his elimination. So what the Hoffman elimination does is it's gonna follow the same kind of thought process of, you know, if you take an alcohol, you know that you can treat that with acid and heat, and what you end up making is the alkene product. So we're gonna kind of follow the same strategy with this, just using an amine instead of the alcohol. Okay, so what you typically do is you take the amine, and then we're going to directly alkylate it as much as we can. So we would use an excess of, say, methyl iodide. And as we talked about, what that'll do is it'll make the quaternary ammonium species. And then we're going to treat that with some sort of a base. And a lot of times they'll use silver salts for this. But what ends up happening is you get elimination of that big nitrogen leaving group. So, as with any elimination, we have the possibility to get two different products. So I want to investigate that a little bit with you now, is which of these predominates and why. And to do that, I'm going to take you back to some of your very early Chem 420 days. And we're going to look at this from a couple different perspectives. I'm going to first represent the this quaternary species as a sawhorse, and then we're going to convert that into Newman projections to really get a look at what's sterically going on here. Okay, so it's probably been a little bit of time since you've done that, but we'll take it slow. And I think, let's see. So I think I'm gonna draw this, maybe, we're gonna have a look at this in two different ways. So I think the first one, let's see. So in order to get that less substituted alkene, let's draw, we're going to look along the C1, C2 bond. So on the carbon 1, you have nothing but hydrogens on it. On carbon 2, you're going to have a hydrogen, the ethyl group, and then the nitrogen group. So kind of the way to orient yourself is like this. C1, 2, 3, 4. This is C1, 2, and 3, 4 are over here in the ethyl group. Okay. But you'll notice So mechanistically, this is going through an E2. So what's going to come into play here is that, if you remember, there's a specific geometric requirement for E2 reactions. Do you remember what that was?
They have to be opposite of each
Yeah,
other.
the hydrogen you're grabbing has to be opposite the leaving group, right? What we call an anti-periplanar
Yes, I would.
type
That's the word.
geometry, or anti-coplanar, however you want to call it. But, so the point is, this is the hydrogen that I'm going to take because my leaving group is anti to it. Right? So let's go ahead and draw the sawhorse diagram for the other one. All right, so the sawhorse diagram for the other one, I'm really paying attention to the C2C3 bond. So I'm going to draw those kind of in the middle. So that's 2 and 3. Off of the C2, you've got the methyl group, which I'm just going to draw like this, I think. You've got a hydrogen, and then more importantly, you have the leaving group. C3, you've got 2 hydrogens and a methyl. One of those hydrogens has to be anti to the leaving group, so that's why I'm drawing it kind of down there. Okay, so that would be my C1. The 2, 3 is in the plane that we're looking at, and then the 4 is up there. So what I'm going to do now is convert both of these sawhorse diagrams to Newman projections. Looking down that bond, and it doesn't really matter, but I guess we'll just look down this bond here. Do y'all remember doing this? Is that ring a bell? Okay, so we're looking at C1, so that's kind of what's in front here in the Newman. And C1, what it has connected to it are just 3 hydrogens. So H, H, H. Then in the back, C2, what it has connected is an H, that ethyl group up here, and then the big leaving group down there. And as you can see, you have the hydrogen that you're losing that is anti to the leaving group, which is what we need for E2 eliminations. All right, moving over to the next one, do the same thing. So now we're looking down at the C2. And what's connected to C2 is up at the top, you've got the big leaving group. You have a methyl group over here, and a hydrogen there. And then kind of in the back, you've got a methyl group, a hydrogen, and a hydrogen. And again, you've got the big leaving group and the hydrogen anti to each other. Which one of these is better? Yeah, why do you say that?
I think the left one has that, kind of like couch strength.
Yeah, so remember, when you're doing these, there is that 60-degree interaction, right? Look, you've got a big methyl and that giant ammonium species that are kind of getting in each other's space. And that is what we call that gauche interaction. And if you look at the one over here on the right, you don't have any gauche interactions.
Isn't it there? You just can't see it because of the way we're looking at it?
No, I mean, in this conformer, you're not going to get any gauche interactions. So the point is that if it picks from this carbon, it's a lot less sterically encumbered than if it picks from the center carbon. All right? And what that leads to is a preference for that double bond, the less substituted. Remember, these had names, by the way. What do we call the more substituted double bond? The Zaitsev product. What do we call the less substituted? Oh, look, it's the Hoffman. So that's where that came from, right? That's why we call it the Hoffman double bond, because it's what is favored in the Hoffman elimination. This is really the same thing, this whole idea of using sterics to control the regio selectivity. This is nothing different than what you've already learned, right? If you were trying to do this reaction, you know that there are two possible ways that that bromide could eliminate. It could eliminate to give you the Zaitsev, or if you wanted to, you could eliminate to get the Hoffman. And what did you do if you wanted the Hoffman?
Bulky base.
Yeah, you used a big, bulky tert-butoxide base. That's the same thing we're doing here. It's just instead of using a really big base to get the Hoffman product, we're using a really big leaving group to get the Hoffman product. It's the same concept, just from kind of a different perspective. So let's go ahead and see if we can practice this. So let me give you, let's do a predict the product here. So if we take this amine and we treat it with excess methyl iodide, it's going to give you the quaternary ammonium. And from there, you have a choice to make, because there are a few different protons that we could potentially grab that will do the elimination of the big leaving group. So take a minute and see if you can first identify I think by my count there are 3 possibilities. There are 3 hydrogens that you could pick off that would give you a viable elimination here. So see if you can find those first. Anybody found one? Here? Yeah. Yeah, that would be one. I'm gonna color code these, I think. Anybody else?
The top left
Here?
point, yeah.
Yeah, I think that's one. One more. Where else could we grab a proton from?
The adjacent one? The one in the middle?
This one?
No,
This one?
Yeah.
That's not gonna, we're not far enough away. Right, you've gotta, cause you have to, the hydrogen that you're pulling from has to be able to push in to eliminate the leaving group.
Then the one in the methyl group.
That's still not far enough. I think,
Right below where
yeah, I think that one, huh? So let's see what those products are gonna look like. So, if I grab proton red, we get that. If I grab proton blue, I get that. And if I grab proton violet,
Wait, which one's blue and which one's violet?
Yeah, the
oh,
one
they're not coming out very well. Blue is the top,
Okay, thanks.
and yeah, maybe I'll switch this to green, you know, be clear. Okay, then green is gonna give me so those are the possible elimination products. Which one is the Hoffman?
Green?
Yeah, the least substituted, right? So we would expect this to be the major product. All right. Okay, so we have one last kind of class of reactions to get through. We'll start talking about it a little bit in lab today, and then we'll really get into it in lecture on Wednesday. But I think that's a good place to stop. So I will see y'all in about 10 minutes.